but I don't think I am. All right, Module 7. We are going to be looking at the second half of Module 7, which is going to be centroids. So the first half was looking at friction. We had done that the last time we were together, and now we're going to be looking at centroids. You'll notice down here in our practice problems, I do have separate practice problems specifically for centroids. So we have some for friction, and now we have some for centroids. So this is the one module. There are two sets of practice problems just because they're kind of very different subjects. We're just kind of sneaking this one in here at the end. But you do have one set of application problems. So there's going to be some that are going to be from the friction portion of our module and then some from the centroids, which we're going to be going over today. So going into our learning plan, we're going to scooch down. And on number 4 here, we are going to be looking at a handout for chapter 9. We are only going to be looking at centroids of simple shapes, which is going to be just pages 180 to 192. All right, that's just the first section here. Additionally, we're going to be working out of our guided notes here for the centroids. So if you're in class, I have these available for you up here. If not, then you'll be following along virtually. As I go back, I'm going to go underneath our camera. I do have my guided notes here underneath my camera. So we're going to be using this, as we reference that chapter 9 handout. So this is our last section here. Like I said, it's centroids. This half of module 7, we are not using the McGraw-Hill ebook. Okay, it's going to be that handout that's there out of that same text that we've seen a couple times here throughout the course. So centroids or centers of gravity and centroids. We've already kind of looked at centers of gravity on items where we have a distributed load and we want to present a concentrated load so that it has the same net effect on a body. So if we look here at just a generic beam, it's 6 feet long. It says here that it's 5 pounds per foot. So what that means is the weight of that, if I would take individual 1-foot sections that I would cut off and I would put them on a scale, each one of those sections by themselves would weigh 5 pounds. So now, since there are 6 feet here, we can multiply 5 pounds per foot times 6 feet, and we're going to get a total weight of that whole beam of 30 pounds. Now, what we can do with that, you'll notice that we have all these little arrows here. That's going to signify that there is what we call an evenly distributed load. And when we have an evenly distributed load, we can break that into a single force at the geometric center in order to have the same net effect on the body. So what we've seen that we've done, I think that was in module 4, I'm pretty sure right at the end of module 4, we would make an equivalent load, as we would call it, and we would take that concentrated load of 30 pounds, the total weight, and we would put it at the geometric center. So since this is a 6-foot long beam, the geometric center would be 3 feet. Now this only works when we have what we call homogeneous beams. That means that it's the same cross-sectional shape, and it's the same material throughout the full 6 feet. Okay, then we can put this equivalent load here. Now, when we have shapes that aren't easy to find, okay, then we're going to have to learn a process, and that's what we're going to be working on today. So this is kind of easy stuff, all right, but it's kind of an overview of a peek at what we can do with centroids and centers of gravity. Now, centroids of a plane area. Centroid of a plane area is when we have the centroid and the center of gravity are at the same point for homogeneous bodies. So if we look at, for instance, on page 183 of that chapter 9 handout, you're going to notice that we have a couple of geometric shapes here. In the case of the triangle, the circle, and the rectangle, you'll notice that for the triangle, we have what we call an axis or a line of symmetry. And all that means is on either side of that vertical line going down, what looks like the center of that triangle, if we would take a mirror image on either side of that line, it would be symmetrical or the same shape on both sides. What that means for us in terms of centers of gravity is that somewhere along here, the center of gravity or the centroid, meaning the same point when we have homogeneous shapes, which is an assumption for what we're going to be looking at, somewhere along that line, the center of gravity is, or the centroid. And that's going to be the point where we can actually put all of the weight for that cross-sectional area. Another way that we could think of it is that's the point where we could balance it as well, okay? And we wouldn't have it, you know, like toppling or anything like that. That's when we have one line of symmetry, or axis, sometimes referred to as symmetry. When we have two lines of symmetry, we find an intersection point, and at that intersection point is where the centroid is. So circles will have two lines of symmetry, horizontal and vertical, and at that intersection of those two lines is where the centroid is going to be. When we have a rectangle or a square, same thing. We're going to find the halfway point up or the halfway point over in either case, and where the intersection point is for those vertical and horizontals, that's where the centroid is going to be, okay? We can also find the centroids of common simple shapes by, you know, just finding them or looking them up. So there's lots of different tables. You can Google this. I'm sure that you have in your math books prior to this, and even in our McGraw-Hill book in the appendix, you're going to find that there is going to be a standard list of, in this case, areas and simple shape, or areas and centroids of simple shapes. So they're going to give us the simple shape, in this case, of a rectangle. They're going to let us know what the equation is to calculate the area. So probably know this already, base times height. And then as far as X bar and Y bar are going to be the locations horizontally and vertically from a known side or axis that it identifies in the shape. And in this case, X bar is going to be the base, which is that horizontal distance, divided by 2. So half of the base is going to be where X bar is. X bar is going to be the location of the centroid that is going to be along that line. Then we're going to find the Y bar. The Y bar, as we look at the height, is going to be halfway up that distance of that height. That's going to be the placement of that line of symmetry or the axis of symmetry. Where those two intersect is going to be our centroid. For things like rectangles, circles, really easy to find, okay? You might need to, but you're going to get used to it. You might need to, you know, look up where's the centroid or what is the area for a triangle, because it's probably something that's not quite at the tip of the tongue. But the area is going to be the base times height divided by 2. And then they identify the base and the height for this triangle. And then as far as the X bar and the Y bar, I always like to say we go from the high side. So for instance, for our height here, the Y bar is going to be 1/3 of that total height. And it's going to come from, if you would, the base or the wider part of the triangle. When we do our X bar, you're going to notice that we have the high side and the low side. It's going to be 1/3, if you would, of the base, or from the high side is going to be where our X bar is going to be. We'll have a couple instances we'll be able to apply that, but this is where we would go for the simple shapes. Then they have a semi-circle and a parabolic spandrel. I don't even know what that is, but these two we really won't use. It's going to be these top 3 for the simple shapes of the composites that we're going to be looking at. So in this chapter, our focus is to develop a process that you can go through in order to find not the centroids of simple shapes, because that's easy peasy. We want to look at composites. So the first example that we're going to be looking at here, all right, I'm going to turn the page, is going to be example number 9.1. Now, in example number 9.1, we are going to be finding the centroid for the composite shape that we have here. And if we look at page 184 in that handout, the original figure is right up here in the corner. And what we want to find is, where is the centroid of this composite shape? Now, a composite shape is simply a shape that is made up of multiple simple shapes. So you'll notice here that we have a rectangle as a base, and they're calling that shape number 1. They have a circle here. This is a hole. So this is going to be, if you would, negative area, or area that we're taking away in order to create the shape. So that's going to be a hole. And then we have a triangle at the very end. So we want to find where is the centroid of this composite shape. And we'll go through the process that we see at the top of the page here. So as we look at section 9.5 in that chapter, we have a couple equations that we are going to use throughout our process here. We're first going to find the total area that is present for our composite shape. So when we refer to area 1, 2, and 3, that just refers to the different areas that we're combining in our composite shape. So for instance, we're going to be breaking our composite shape into 3 different shapes. We've got a rectangle, a circle, and a triangle. So the areas then would go along with each one of those different simple shapes. Then to find the X bar, we're going to multiply the area of shape number 1 times its X distance to the centroid from the reference axis. So for instance, when we look at the rectangle, the X distance is going to be horizontally, where is the centroid just for the rectangle in relationship to what we call our reference axis. This will make more sense when we do our example, but that's going to be the X value. So we take that area, multiply it by each one of the respective X values. So we've got an A1 times X1, an A2 times X2, and an A3 times X3. And then we're going to divide it by the total area, okay? And that's going to give us our X bar from the reference axis. Then we're going to do something very similar, but this time we're going to take the Y dimensions to the centroid of each one of the corresponding individual shapes. So we're going to take area 1 times Y1 plus A2 times Y2 plus A3 times Y3 and divide by the total area again to get the location of the Y bar. Now, what are X bar and Y bar? They are the location of the centroid on the complete composite. So when we get to the X bar, Y bar, that's going to be like our final answer for these problems. We want to find where the centroid is for these composite shapes. So this evening, we're going to be doing 2 complete problems that'll then help you with the 2 problems that I'm going to have you do for your application problems for this section. Okay. So our first example, as I kind of alluded to already, is we're going to be looking at this example 9.1. And they want us to find the centroid. Identify X bar and Y bar for this composite shape. So step number 1 is to identify your reference axis. Now, I think in both the problems that we're going to be doing this evening and in the 2 application problems, you have a reference axis identified. If it's not, you need to pick it, okay? In this case, our reference axis is going to be the X and the Y axes where they come together in that lower left-hand corner of our composite shape, okay? So you want to identify that or define it, okay? So it's going to be that X and Y of the entire composite. This is important because all of our dimensions for the individual shapes are going to come from the reference axis, okay? And that'll make more sense again when we start looking at the individual shapes. Then we want to label or pick our simple shapes. Now, in this case, in our example, as we saw, they've already identified number 1 is going to be our rectangle. Number 2 is going to be our hole or our circle. And number 3 is going to be the triangle. Okay. So now throughout, we're going to use kind of the 1s, the 2s, and the 3s, like we saw up here, to identify which shape and which dimension X or Y that we're referring to, shape number 1, number 2, or number 3. And then we're going to turn the page and we're now going to look at the individual shapes. Okay. Now, step number 4 says draw each shape with the reference axis or that origin. So the first shape we're going to look at is number 1. This was the rectangle. Okay. Now the rectangle, in regard to the reference axis, if you recall, you're going to see that we have the reference axis here, and it's going to run down to that lower left-hand corner. So I'm going to simply highlight the reference axis again, and we're going to place our shape so that it's in that same place as the original composite. And it happens to be, snugged right into that bottom left-hand corner. So this is shape number 1. It says here, identify and dimension the centroid of the individual shape with relation to the reference axis. So if we just kind of sketch in the middle here, this is going to be our centroid number 1, or the centroid of shape number 1. And now what we want to do is we want to add dimensions, and we want to reference where that center is located from the reference axis. So we got to go back to our original shape. Now, on the sketch that I made, I don't have the dimensions, but the dimensions are on page 184. And you'll notice that our rectangle is 6 inches high. Scooch in here just in case you want to see that. 6 inches high and 7 inches long. Okay, and then the 0, 0 is down here in the lower left-hand corner. So if I turn this over, I go back up here, we know that the length is 7 inches and the height is 6 inches. Okay. So now we want to dimension where the centroid is for this shape from the reference axis. Since our reference axis is running along the left-hand side and the bottom, we want to show our x1 is going to be the horizontal distance. I like to say it's the distance from the y-axis is going to be our x dimension to the centroid. And then our y1 is going to be the distance from the horizontal axis up to the centroid. Notice that I used the numbers 1 next to the x and next to the y. This is going to then tie it to shape number 1. Okay. Now we want to gather information about our shape. So I'm going to skip over area for right now because we already identified our x1. So if our x1 is the distance from the reference axis on the left-hand side here to our centroid, and if the total length of our shape is 7 inches, what is x1? Somebody in the room knows what x1 is.
3.5 inches.
3.5 inches, yes. Remember that day when I called on people randomly? That might be today again. It's our last lecture. Maybe we'll do it again. Pressure's on. 3.5 inches. Yes, 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 yes. So what is going to be my y1? If 6 is the height, Josh, but what is it? 3 inches. Yes, 3 inches. And then we have to calculate our area. This is a rectangle, so we're expecting it to be base times height, right? So that means that's going to be our base is 7 inches. Our height is 6 inches. So that means that's going to be 42 inches squared. Okay. So for each one of our shapes, we are always going to collect area, x, and a y. Okay. Area, x, and a y. Again, here, kind of that statement I said earlier, distance of the centroid of shape number 1 from the y-axis is your x1. The distance of the centroid of shape number 1 from the x-axis is going to be your y1. Okay. All right. I'm ready to move to the next shape. You have to do this 2 more times. So now the next thing you want to do is you want to identify your shape in reference to the reference axis. So here's my reference axis again. I need to find where the centroid of my circle is in regard to the reference axis. So just like I had for the last one, I am going to have a y2 this time. That's the distance up from the x-axis. And then I'm going to have an x2, which is going to be the distance from the y-axis to the centroid. Okay.
Kelly, could you go back to the previous page real quick?
I can. What you need?
I just wanted to make sure I had the correct equation written down. For the A1.
Oh yeah, base times height. It's a rectangle. Yep.
Yep.
Good. Good, good, good. So now as we look here, we're going to have to look back at our illustration to see, did they give us dimensions for the centroid or the center location of that hole? And they did. You're going to notice that going up from the x-axis, which would be our y1, is going to be 3 inches. I'm sorry, y2. We're on shape number 2, y2. And then it's going to be 3 inches is going to be x2. So down here, 3 inches. 3 inches. Okay. Now, area of a circle. Okay, area of a circle. There are 2 of them, right? What are they? I've got pi r squared, Alex said. Yep, there's pi r squared. And what's the other one?
Pi d squared over 4.
Yes, pi d squared over 4. Now, if we look back at the figure, you're going to notice that it's a hole has a radius of 2 inches. Since we're given the radius, we might as well use the pi r squared equation. If we were given a diameter, we could use the other one, but usually we can divide by 2 pretty efficiently. So, so we are going to use the 2 inches. So this is going to be pi times 2 inches squared. Okay. So my area 2, what do we get for area 2? You get 12.566 inches squared. There's something we're missing. Anybody think what might be missing? This is the right number. Go ahead, Tyler.
Since we're removing that area, we have to put in a negative.
Yes, since we're removing the area, this is a hole, remember, we need to put a negative in front of our area. So yes, this is a negative or a takeaway. So it takes away from, if you would, the total area. So we need to remove it. So a negative goes in front there. We do not use the negative sign for the X or the Y though, because that is location, if you would, in the first quadrant, but up and to the right of our 0, 0 or our X and Y axes. Okay, so those are okay. If we would go to the left or down of our reference axis, then we would have negatives, and that would be direction, okay? All right. Next shape, go ahead and do this one on your own if you need to. I'll put the little illustration here. So if you need information, see what you can fill in for your triangle, hopefully. You can see that who are virtual or in the classroom. Okay, as we start looking here, I just want to start filling some of these items in. If we look at the area number 3, this is a triangle. So if you do need to reference, you can always go back to, finding somewhere just a generic table, but in that appendix, page 2, we have the area of a triangle is going to be base times height divided by 2. So I have that here. The base of our triangle is going to be vertical in this case, and then the height is going to be horizontal, all right? If we look back at our illustration, the total height here is going to be 6 inches. It's 3 and 3. So it's a total of 6. And then the base is a total of 6. The height is going to be 3. So we're going to have 6 inches times 3 inches divided by 2. So if we multiply 6 times 3, we get 18 divided by 2. That means we're going to have 9 inches squared, right? Let's look at X3. X3 is the centroid of our triangle. Now remember, all of our X distances for the individual shapes have to come from the reference axis. So the location of our centroid has to come horizontally from the y-axis. So we have to take 7, because that's where our triangle starts. That's where how long that rectangle was. And then this is going to be 1/3 the height, the overall height here of 3. So this is going to be 7 inches plus h over 3. So it's going to be 7 inches plus 3 inches divided by 3. So we should get 7 plus 1. 8 inches is going to be our value for our X3. Okay, so again, from the reference axis, do not put 1 here. Don't just put the, from the shape bottom. It has to come back from the reference axis that we identified at the beginning of our problem, or was given to us at the beginning of our problem. And then Y3, okay? Now Y3, in this case, you're going to notice that there is an axis of symmetry that runs right down the middle, if you would, of the peak of that triangle. And that distance from the x-axis is 3 inches, right? 3 inches. Okay, any questions here? There's a little note. It says, remember, all of your x and y's for each one of the shapes is always going to be a distance from that reference axis you set in step number 1, or was given in step number 1. All right, good. Turn the page. Now we've got each one of our shapes done. Now what we're going to do is we're going to organize this information, okay? We're going to organize the information, and we're going to organize it based on what we need. If we go back to the equations to calculate x bar and y bar, we're going to need the values that we have here. So we're going to need each one of our areas, and we're going to need the total area. As you know, each one of those symbols in front of the a times the x and the a are the summation. So I think it's capital sigma in the Greek alphabet. So we're going to add up all of our areas times our x's. We're going to divide by the total area. Okay. So that means on our chart here, this is just a way to kind of organize the numbers we were collecting for each one of our shapes. You're going to notice that we have an area column for shape and then a row for 1, 2, and 3. And then down below, wherever there was a sum that we need for our x bar, our y bar, I've got a little cloud and we'll fill that in. If we don't need the sum of that column, I put an X in there, okay? So we're gonna need a sum column for the total area. We're gonna need a sum column for the a times the x values. And then we're gonna need a column for the areas times the y values, okay? So go ahead and from the information that we had just collected on those 3 previous shapes, fill in the chart that you see here. And don't forget, for shape number 2, that's a hole. So the area needs to be negative, just like we identified. Okay. So go ahead and fill in, and then we can compare. I do have the units at the top of the column, so you don't need to include those in the cells if you would. Looks like most people are done or finishing up. You should get a total area of 38.44, total A times X, 181.32, and then A times Y's are 115.32. Now at the top are the units for each one of our columns. So as we know, area is inches squared in this case. We multiply it by X. We're going to take inches squared times inches. So inches cubed is the A times the X. And then the same thing for the A times the Y. Okay. Now we're going to go down and we're going to calculate those X bar and Y bars. So again, the overall total, if you would, centroid locations for our composite area. So we're going to look to the summation of the A times the X's. So we're going to go up to our column here. This is 181.32, and you're going to add the units. This is inches cubed. Go in the top here. Divided by the total area. So that's going to be that first column, 38.44 inches squared. Okay, inches squared. So now as we look at our units here, this is where we're going to cancel. The inches squared are going to both cancel on the bottom. 2 of the inches cubed on top. So there's still inches left over on top, right? If we're trying to find a dimension or a distance, X bar, it does make sense that the final units should be inches, right? What do we get for a value here? If we take 181.32, we divide by 38.44. I'm going to say 17. Okay. I'm going to add a decimal. So 4.717. Yep, you got it, Gabrielle. Thank you. Okay. Now what we're going to do is you're going to do a similar thing, but this time we're going to take the A times the Y's divided by the total area. So we go up to that last column, 115.32 inches cubed, divided by 38.44 inches squared. So our inches squared are going to cancel down here, 2 of them with 1 left over inches. So 115.32 divided by 38.44, you should get exactly 3 inches. Okay. That should be no surprise. Okay. And the reason it's no surprise is because, first of all of our Y's were 3. And if we look back at our composite, very first here, you're going to notice that we have a common, what we would call like an axis or a line of symmetry, where on either side of that line, it's a mirror image. It's symmetrical. So our centroid is going to always lie somewhere along there. Now, I didn't let you know that ahead of time. I thought, why not go through and compute it? But then we also see it actually come out. So if you see a line of symmetry, you can state that by inspection rather than doing the calculations, but you can see the calculations are going to come out, you know, when we see that line of symmetry to its actual number. Okay. If it doesn't, then you might have done something wrong. All right. So then the very last step then on all of the problems, this problem, the next one that we do in class here, but then also on the 2 that you do for your application problems, I want you to show me what your numbers mean here. And you don't have to scale it. You don't have to draw a CAD diagram, but proportionally place the centroid. So X bar is going to be the horizontal distance, the distance away from what would be the Y axis. Now, if you recall at the center of our circle, that was 3 inches from Y. And then this is a radius of 2 inches. So that means the edge of the circle would be to 5. Our value is 4.717. So it is going to fall on that axis of symmetry somewhere between that center of that circle and the actual edge of the circle. Don't draw it on the outside because that would be past the value. So this distance right here is my X bar, okay, which is equal to 4.717 inches. And then my Y bar is equal to 3 inches, going straight up, okay? So make sure that you always draw your diagram, letting me know that you understand what these values mean. Now, because both of these values are positive, that means they're going to be to the right of the y-axis and up from the x-axis. If any one of these numbers was negative, which can happen, then that just means that you're on the opposite side or in the negative direction on either side of those axes. Okay? Questions? All right. How many have kind of done this process before? Yeah. All right. So again, it's a review. You're going to be going deeper into this at the beginning of your mechanics of materials, material mechanics. Oh, solid mechanics. It's called solid mechanics. It's like a strength of materials. That's how I refer to the class. And they're going to be looking at this and moments of inertia in that class as well that you'll be using throughout. All right. So let's do another one because we want to get practice. Okay. Our next example is going to be example 9.2, and that is found 9.3. I'm out of order here. Sorry. Oh, it's over here. That's fine. 9.2 is at the top of page 185. And here we have a cross section of the model of an arched dam is shown. And so that's right down here. So this is the cross section that we're looking at. Our reference axis is going to be here along the Y and the X. And they have this broken into three shapes. One, it's going to be the tall rectangle. Then two, short one on the left-hand side of the y-axis, and then our triangle, okay? We want to determine what the centroid is of this composite shape. Now, in this case, these are going to be three additive simple shapes. So we're not going to have to worry about a negative in this case. There's no hole or material that's being removed. So as far as process-wise, I am not going to redraw the composite. We are just going to keep it together right here. And you'll notice that I identified, or they identified for us, our reference axis, which I just highlighted, okay? So now what we're going to do is we're going to do the same steps that we did for the previous problem using the information that we have here. So I'm going to go to our guided notes, and it says here, draw the composite shape. Again, it's already identified. You don't have to redraw it here. We're just going to use the figure that we have in the problem statement on page 185, okay? And then it wants to identify each of the simple shapes, which we already have. Again, shape number one is going to be the tall rectangle, the 90 by 450. Number two is going to be the 60 by 90. And then shape number three is going to be the 90 by 60 triangle, okay? Now, we are now going to look at each of those individual shapes. So shape number one, going to be here. Draw each shape in relation to the reference axis. So shape number one is the tall rectangle. It's 90 millimeters to the right of the y-axis, and it's 450 up. So I'm just going to grab my straight edge here. I'm going to draw that tall rectangle. And again, I like to highlight the reference axis. You don't have to on your problems at all, but it just helps to keep track of that. So I know that this is 90 millimeters wide and 450 millimeters tall. For shape number one, I'm just going to sketch in where I believe about that centroid is going to be, and it's going to be called centroid number one. Okay. And now we want to dimension the location of our centroid with respect to our reference axis. So our x1 is going to be a distance from the y-axis to horizontally to the centroid. Okay. And we can see here that x1 is going to be the base, if you would, of that rectangle divided by 2. The base of the rectangle is 90 divided by 2. So I'm going to put 45 inches for x1. It is millimeters. I was in inch mode from the last example. Millimeters. Thank you. Now the y1 is going to be the distance from the x-axis here, our x reference axis, up to the centroid number 1. So this dimension right here is going to be our y1, which is going to be equal to the height divided by 2. So the height is 450 millimeters. So 225 millimeters is going to be the distance y1. Area of a rectangle we know to be the base times the height. So that's simply going to be 90 millimeters times 450 millimeters, the total height. Now, this is going to be kind of a big number, okay? So if we take 90 and 450, it's going to be 40,500 millimeters squared. In the book, what they did is they showed 40.5 times 10 to the third millimeters squared. So they are using the scientific notation, okay? So if you wanted to use all the zeros, you certainly can, but it just makes it a little bit easier, you know, with the amount of zeros and how, you know, big it gets, because we're going to find that we're going to have some bigger numbers in this example as well because of the millimeters. Okay, so that is shape number 1, area, X and Y. Let's look at shape number 2. Shape number 2, zoom back in here, is going to be right here. So it's on the left-hand side of our y-axis. It's a rectangle that's 60 millimeters high, and it would be 90 millimeters wide. Okay, so we're going to draw a rectangle, and its lower right-hand corner is going to be at that 0, 0. Okay, so this is 90 millimeters, and the height is going to be 60 millimeters. Centroid number 2. Its distance horizontally from the y-axis, in this case, is going to be on the left-hand side, and this is going to be x2. So if the width of that rectangle is 90, half of that is 45, but x2 is going to be a negative 45 millimeters because it's on the left-hand side of the y-axis. Does that make sense for everybody? Okay. Our y2 is going to be a distance from the x-axis up to the location of our centroid. So y2 will be here. It is going to be half the total height, which is 60 millimeters. So this is going to be 30 millimeters. Even though it's on the left-hand side of the y-axis, it is up from the x-axis. So it is above the x-axis, so it's in the positive direction on the x. So if you would, in the second quadrant. And then we need to do area. So we know that to be base times height. So it's going to be 90 millimeters times 60 millimeters. So if we take 90, it's going to be 5.4 times 10 to the third millimeters squared. So 5.4 times 10 to the third, or 5,400 millimeters squared. Okay, any questions on those two? All right, let's turn the page. And now we're going to put our last shape. Our last shape is the triangle number 3. It is 60 millimeters high, 90 wide, and it's going to start at the top of the previous rectangle number 2. Okay. So centroid will be right about here. So this will be C3. The distance from the x-axis is 60 millimeters, as we know. Okay. Now the distance up to our centroid here is going to be equal to the height of our rectangle divided by 3. Okay, divided by 3. So the height of our rectangle we know is 60, right? So that's going to be 60 divided by 3, 60 millimeters divided by 3. So this distance right here is going to be 20 millimeters, right? That is not Y3 yet. Y3 is going to be 60 millimeters plus 20 millimeters, right? 60 to the bottom of the rectangle or the bottom of the triangle, and then another 20. So 60 plus 20, Y3 is 80 millimeters. See that? X3 is going to be the distance from the y-axis to that centroid. So this is going to be X3. Now X3 is going to be equal to the base divided by 3. We know the base was, I'm going to put it here, 90 millimeters. So my base is going to be equal to 90 millimeters. Oh, I don't have room there. I'm going to have to put it by the X. So base divided by 3 is equal to 90 millimeters divided by 3. It's kind of easy, right? 30 millimeters. But am I forgetting something?
Negative.
Negative, Tyler says, because it's on the left-hand side of the y-axis. So don't forget your negative here for the X3. And then the area. Area is base times height divided by 2. So the base here is going to be our 90 millimeters times the height of 60 millimeters again, divided by 2. So 2,700 or 2.7 times 10 to the third millimeters squared. So again, area, X and Y for each one of the individual shapes. And then those X's and Y's are measured from the reference axis. Okay. Now that we have our 3 shapes and we have all the data collected, we now can fill in our chart. So go ahead and do that for the information that we gathered for each one of these shapes. And then also do your sums as well as your multiplication, like for the A times the X's and Y's. I didn't double check my numbers, but I'll zoom in. And hopefully yours are matching mine. Once we have our totals for the columns that we need for the X bar and the Y bar, go ahead and fill in for X bar and Y bar and see what you get. Do my numbers and anybody else get the same numbers in my columns? Okay, it just as a quick confirmation. Okay. So now if I go down and I'll kind of keep this up here. So if you're still doing a little calculating, okay. My X bar is going to be the total of the A times the X column. Okay. So that's going to be 1.4985 times 10 to the 6th millimeters cubed on top, divided by the total area, 48.6 times 10 to the 3rd, okay, millimeters squared. The millimeters squared cancel. I'm left with millimeters, which makes sense for a distance. So if I take should get 30.83 millimeters. Is that right? And then for our Y bar, we're going to take the A times the Y total. Divided by the total area. 48.6 times 10 to the 3rd. Millimeters squared. Millimeters is left. 1, 2, 3, 4, 6. Okay. Should come up with 195.28 millimeters. Okay. Sounds familiar. All right, so now you're going to notice that we have positive values for each of these. So all that means is that we, in reference to our reference axis, we are going to be to the right for the X bar, and we're going to be up for the Y bar. Okay. Again, if either one of these numbers would be negative, it would be on the opposite side, of the axis. So now the last step here is to label your X and Y on the diagram. I know it kind of went off the page a little bit. So if you want to just darken in that X axis, here's our reference. Okay. Now you could redraw, the whole rectangle with the triangle if you wanted to, but our centroid is going to be closer to that Y axis. Okay. And that means that our X bar, which is equal to 30.83 millimeters, is going to be on the right-hand side of that Y axis. And then our Y bar is going to be up from what would be the X axis. And that's going to be 195.28 millimeters. And then this would be your centroid. Okay. So are there any questions at all about the process or, how to do the final calculation, fill in the chart, make sure that you do a diagram that is required at the end of each one of the application problems that we have for this section? Okay. All right. Well, if not, those are the two problems. You'll notice that there are a couple more pages in our handout here, but you can skip the last two examples. Okay. If we go back to practice problems for the centroids in module 7, you will notice that I said only pages 1 to 7, only examples 1 and 2, skip examples 3 and 4. Okay. So just have a couple extra pages there. You don't need to fill in. So you don't need to make copies of those or scan those in when you submit, just the ones that we did. Okay, so that'll be your practice problems. Now let's take a peek at the application problems. So if we go into Module 7 application problems, this is going to be the second section down here. There are two problems. These two problems are from the handout for Chapter 9. So again, that PDF that is in the learning plan, we're going to go to page 191. And there are two problems there that you're going to be doing. Now, I did add for you the final answers that you should achieve, for each one of these. So those are located, and each one of these problems is 15 points. The ones above are 10 points each. These are a little bit longer, so I gave you some extra points on this. So, so same format that we did for the practice problems. All right, so make sure that you go through and you follow that same formatting, including making a diagram at the end of where your X bar and your Y bar are. So the two problems you're going to do are number 9, 10. They identify the reference axis for you, so you don't need to find one. I just have the final answers. I put them on here as just a note for myself. And then you'll notice that this is the composite shape, and you want to find the X bar and the Y bar. The other one that you're going to do is going to be 9, 12. This one's also in millimeters or in metric units. And then you're going to want to find the X bar and the Y bar from the reference axis that's identified there. Okay. Same process, same requirement. Don't forget your diagram at the end where you label your X bar and your Y bar. Okay. Questions? All right. Now you are ready to finish up this last assignment in statics. Okay. So, so I am going to stop the recording here.